Hello everyone. So in the last class we were talking about the Kolmogorov spectra. We started assuming, so let's say there is a power spectrum where you have E of kappa is A kappa to the minus P, where A and P are constants. And then we derived the kinetic energy and the dissipation associated with this spectrum. So when we take the kinetic energy, we have to take the energy contained in the wave numbers larger than kappa. So that means because the energy is going from the large scales to the small scales, when we consider the energy contained in the wave numbers, we have to consider the energy contained in the wave numbers greater than kappa. Whereas for dissipation, since dissipation happens, it increases with increase in wave number. So the dissipation happens at the smaller scales, at the larger wave numbers. So because of that, we consider dissipation in the wave numbers less than kappa. We consider dissipation in wave numbers less than kappa. So dissipation would be integral 0 to kappa. On the other hand, turbulent kinetic energy would be integral kappa to infinity. That's what we have here shown in this first integral and in this second integral as well. Once you derive that, we realize that both these integrals can only converge for certain values of P. That is, if P is greater than 1 and if P is less than 3. So if P is equal to 5/3, that comes between 1 and 3 and it satisfies the Kolmogorov spectrum. So for this value of P, both the integrals for K and dissipation converge. So now if we use P is equal to 5/3, then K, the turbulent kinetic energy is proportional to kappa to the minus 2/3 and the dissipation is proportional to kappa to the 4/3. So what does that mean? So as much as the Kolmogorov spectrum applies only to the inertial subrange, remember we were always looking at this spectrum as being applicable only to the inertial subrange, because it is in that range that the energy spectrum depends only on epsilon and not on nu. So it was the simpler range to consider when you're assuming a spectrum. That's the reason why we considered only the inertial subrange. Now, what we made sure is if you have the Kolmogorov minus 5/3 spectrum, which is K to the minus 5/3. Now, if that applies only to the inertial subrange, what we are seeing is that the observations are consistent with the notion that most of the energy is contained in the large scales, isn't it? Because look at what kappa to the minus 2/3 does. Kappa to the minus 2/3 keeps decreasing as you are increasing in wave number, as you're going down in the scales. And look at what the dissipation in terms of kappa to the 4/3 does. It keeps increasing as you're increasing in wave number. So as you're going down in the scale. So that is what this means. Bulk of the energy is contained in the large scales and bulk of the dissipation is contained in the small scales. That's where we were at last time. So that completes what we wanted to talk about in terms of the Kolmogorov spectrum. Now, what we will do is we will restate the Kolmogorov hypothesis in terms of the probability distribution function. So the PDF. So this is just a restatement of the Kolmogorov hypothesis in terms of the endpoint distribution in 4D space. What is the 4D space? 3 spatial and 1 temporal. So x and t, both x and t, x is a vector, so that you have x1, x2, x3 and then time, so that makes it a 4D space. So let's consider a simple domain within the turbulent flow, and let's say you have x0, x1 and so on up till xn be specified set of points within the domain. Now what happens is you have the new coordinates and velocity differences defined as follows. So now you have y is equal to x minus some reference x0 and vy is equal to uxt minus ux0, again some reference velocity. Now, what we are saying is, let's say the joint PDF of V, because that's what we are talking about, right? The joint PDF of V in all these points is denoted by Fn. Okay, so with that as the context, let's look at each of Kolmogorov's hypotheses. According to the local homogeneity definition, which is where all the small scales are homogeneous. So if you have a local homogeneity definition, then the turbulence is locally homogeneous in the domain, right? So if for every fixed n, meaning what? If for every fixed total number of points n and yn, which is the differences, the normalized, I shouldn't say normalized, but the differences in spatial points, so x minus x naught. And the endpoint PDF Fn is independent of x naught and ux, isn't it? That is the local homogeneity definition. It is independent of space. So what we are saying is that the PDF is also independent of space. That's all we are saying. So that is the local homogeneity definition. Now, if you think about the local isotropy definition, this is Kolmogorov's first hypothesis. The turbulence is locally isotropic in the domain if it is locally homogeneous and if in addition the PDF Fn is invariant with respect to rotations and reflections. So the local isotropy means it is statistically isotropic. So they are invariant to reflections and rotations. So that means the PDF is also invariant to rotations and reflections. That's what we are stating here. So that's this local isotropy definition. So we have the local homogeneity definition and the local isotropy definition. Now let's go into the hypothesis. The local isotropy hypothesis. What did the local isotropy hypothesis state? You have anisotropic large scales, then you have small scales that are isotropic, that are statistically isotropic. Now let's see what that means in terms of the PDF. If in any turbulent flow at sufficiently large Reynolds number, we always need to state that the turbulence is to a good approximation locally isotropic if the domain is sufficiently small and is not near the boundary of the flow or any other singularities. Okay, so as long as you are looking at a region that is away from the boundaries and does not contain any other singularities, then your turbulence is to a good approximation locally isotropic, as in it is invariant to rotations and reflections. Now the second hypothesis, which is the first similarity hypothesis of Kolmogorov. For locally isotropic turbulence, the endpoint PDF is uniquely determined by mu and epsilon, isn't it? Everything in the universal equilibrium range, everything below the large scales, all the small scales, they are uniquely determined by mu and epsilon. So that means the endpoint PDF is also uniquely determined by mu and epsilon. Now let's look at the second similarity hypothesis, which is Kolmogorov's third hypothesis. If the moduli of vectors, okay, so ym, so that is that differences, isn't it? X minus the reference point, x minus x naught, as we had shown here. As we had shown this for x minus x naught, so the y is the differences, x minus a reference point. And of their differences ym minus yn, and of their differences as well, are large compared with the Kolmogorov scale, isn't it? So then the endpoint PDF is uniquely determined by epsilon and does not depend on mu. It is uniquely determined by epsilon and does not depend on mu. So this is that dissipation range. This is everything below LDI, isn't it? Everything above kappa di. So if they are much larger than eta, we are saying there is this range that is only dependent on epsilon and not on mu. So this range here is when we are saying the turbulence only depends on epsilon and not on nu, that means the PDF would also follow the same rule. It would also depend on epsilon and not on nu. So that is just a restatement of the Kolmogorov's hypothesis in terms of the endpoint PDF. So next, what we are going to look at are structure functions. So we now have stated the Kolmogorov's theory, their hypothesis, what it means in terms of the spectrum. Now let's look at a new concept which is related to the structure functions. The structure functions, the definition I'm going to be providing here. So Kolmogorov, what in 1941, he developed this concept of using the structure functions, which is basically a second order velocity structure functions that we are talking about. So in 1941, he developed this concept of second order velocity structure functions to apply his hypothesis to something. So he developed the hypothesis. This is a way for him to show the application of those hypotheses. So by definition, the second order structure function is the covariance of the difference in velocity between 2 points x and x plus r. So that is defined like this. So this is the second order structure function dij, which will be a function of r, x and t, where r is the space difference in space between the 2 points. So x and x plus r, isn't it? So r is the difference between the 2 points. So like I said, it is the covariance. So it is ui x plus r minus ui. Remember, it is a covariance of the velocity differences. So it is ui x plus r minus ui x, and then multiplied by uj x plus r minus uj x plus r. So here, this is the second order velocity difference or second order structure function. In terms of the velocity differences, you could write that as dij y2 minus y1 x0 plus y1t, and then you could write that as vi minus vi, isn't it? Vi y2 minus vi y1 times vj y2 minus vj y1, the velocity differences. The first implication of this hypothesis of the local isotropy hypothesis is that dij is independent of x0, because it depends only on its local environment, isn't it? So it is independent of x0. The reference point doesn't matter. The above equation shows that, this equation here shows that dij does not depend on x, and from the first equation dij depends on only r and not on y1 and y2 separately, as in r meaning the difference between the two spatial points. You can also write dij as dijr as dnn, okay, dnn r of t times the Kronecker delta, and then you have dll minus dnn times rj divided by r squared. And if the coordinate system is chosen such that r is equal to e1r, then what you will have is d11 is equal to dll, d22 is equal to d33 is equal to dnn, and dij is equal to 0 if I is not equal to j. So if you choose your coordinate system in such a form, you can sort of derive this. So d11 is equal to dll, d22 is equal to d33 is equal to dnn. Okay, so that is with respect to the structure function. Now let's take that to the 2-point correlation as well. Okay, we know that the structure function can be expressed in that form. This is again an application of the Kolmogorov's hypothesis. So we applied the local isotropy hypothesis to the second order structure function. Now we look at in terms of the 2-point correlation or the autocorrelation function. So again, the Kolmogorov's hypothesis and deductions, as you would have seen earlier, they have no direct connection to the Navier-Stokes equations. Now, when we describe the energy cascade though, the transfer of energy to successively smaller scales is indeed critical, but the precise mechanism we haven't identified yet, right? Kolmogorov's hypothesis talks about that, but the mechanism in terms of the equations, we have not talked about how that happens. So let's let's look at the Navier-Stokes equations in a little bit more detail, and let's see from there if we can try to get some information regarding the energy cascade. So for that purpose, let's consider homogeneous isotropic turbulence, because we want to make our life simple, and so we are just looking at a simple kind of flow. So let's say homogeneous isotropic turbulence. So no spatial variation and no variation with respect to reflections or rotations. And let's say there is a zero mean velocity. That means you're only interested in the fluctuations. Okay, so RMS velocity u prime, dissipation rate, and because of the homogeneity, the 2-point correlation, which is defined originally like this, is independent of x because of the homogeneity definition. So Rij of 0t becomes Uiuj. See, you see how we have simplified it because of those assumptions, the homogeneous assumption and the isotropic assumption. So Uiuj would be u prime squared delta ij, isn't it? So delta ij being the Kronecker delta. So now that you have the 2-point correlation, which becomes the autocorrelation function in the case of the homogeneous definition approximation, now let's look at this in more detail. So just like with the structure function, because of isotropy, Rij can be expressed in terms of two scalar functions. Earlier, we expressed Dij in terms of DLL and DNN. So similarly, we are going to express Rij as u prime squared g of rt, some function, scalar function g of rt delta ij, plus f of rt minus g of rt times ri rj divided by r squared. Now if you choose your coordinate system such that r is equal to e1r, then this equation becomes r11 over u prime squared is f of rt, and r22 over u prime squared is g of rt, and given by this, isn't it? And also R22 would be equal to R33 and Rij would be equal to 0 if I is not equal to j. So essentially, F and G are the longitudinal and transverse, respectively. Longitudinal and transverse autocorrelation functions, respectively. R11 over u prime squared, normalized of course, and R22 over u prime squared, that is g of rt. So those are your scalar functions. We didn't start with assuming that. We said, okay, let's try to express it as two scalar functions, and it turns out that f and g are the autocorrelation functions. So if I plot f and f of rt in grid turbulence, okay, these are actually measurements of longitudinal velocity autocorrelations from an old experimental data of Compte-Below and Courcine from 1971. And as you can see, you have a continuously decreasing autocorrelation function as r is increasing, which makes sense. As you are spacing the points away from each other, your correlation between the velocities is going to keep on decreasing. Now, you can calculate a longitudinal integral length scale by integrating the autocorrelation function. So 0 to infinity f of rt dr, which is basically just the area under the curve of f of rt. Similarly, you can get the transverse integral length scale L22 by 0 to infinity g of rt dr. Now L11 is characteristic of the large eddies, and in isotropic turbulence the transverse integral length scale just becomes half of L11. How is that? We are talking about a problem which is homogeneous turbulence, so nothing is changing with space. That is all okay, but we are also talking about isotropic turbulence, so no variations with respect to reflections and rotations. So that means u1 prime squared is equal to u2 prime squared is equal to u3 prime squared, of course mean of those. So u1 prime squared mean is equal to u2 prime squared mean is equal to u3 prime squared mean. So so what happens is you would have a longitudinal integral length scale, and then you would have a transverse integral length scale which is the same as in both the directions, as in L22 is equal to L33. Just like you had earlier, R22 is equal to R33, so because of that L22 would be equal to L33. And because the flow is primarily in the longitudinal direction, L22 would be equal to half of L33. L22 would be equal to half of L33. That is what, L22 would be equal to half of L11. I'm sorry, L22 would be equal to half of L11. That is what we mean by this one. All right. So we have looked at the structure function, and then we looked at the two-point correlation, specifically the autocorrelation function. Now let's take that forward and define a new scale called the Taylor microscale. The second length scale, we talked about the Kolmogorov microscale or Kolmogorov scale. Here we are talking about a Taylor microscale which is only applicable in homogeneous turbulence. So it is not dealt with it a lot in more very practical flows. So I'm just covering this as part of covering it for as its application to Kolmogorov's hypothesis. So the second length scale is obtained from f of rt, which is the longitudinal Taylor microscale lambda f. So f of rt is an even function with r, okay, and the first derivative at the origin is 0, as you saw, and the second derivative is negative because it is decreasing. So now you have a lambda f which is defined as, this is the Taylor microscale, defined as minus half f double prime, as in the second derivative, the whole thing raised to minus half. So based on the transverse autocorrelation g of rt and the transverse microscale, the lambda g, okay, so we had lambda f, which is the Taylor microscale, the longitudinal Taylor microscale. Now you have a transverse Taylor microscale, which is lambda g, given as minus half g double prime 0 to t, and a whole thing raised to minus half. So you have longitudinal Taylor microscale and transverse Taylor microscale. In isotropic turbulence, lambda g is lambda f over square root of 2. Just like you had L22 equal to half of L11, you have the Taylor microscale in the transverse direction equal to 1 over root 2 of lambda ft. So what Taylor did in 1935 is he defined lambda g and obtained the following equation for dissipation, which is dissipation is equal to 15 nu u prime squared over lambda g squared. He then stated that lambda g may be roughly regarded as a measure of the diameter of the smallest eddies. So it is again on the small scales and is responsible for the dissipation of energy. So it is just another scale which is not, it is not the same as the Kolmogorov microscale, but it is of comparable order as the Kolmogorov scale. Now, what he said was that lambda g may be regarded as a measure of the diameter of the smallest eddies which are responsible for the dissipation of energy. So it turns out that deduction is incorrect because it incorrectly supposes that u prime is the characteristic velocity of the dissipative eddies. We now know that u prime is not the characteristic velocity of the dissipative eddies. U eta is the characteristic velocity of the dissipative eddies. The Kolmogorov velocity, and associated with that is the Kolmogorov timescale tau eta, isn't it? So you have a Kolmogorov scale eta, you have a Kolmogorov velocity u eta. U eta is associated with the small scales, not u prime. So here, as you can see here, he used u prime to derive the dissipation, which was an incorrect assumption at that time. So then, if you consider, so let that be as it may. Let's consider a length scale L, sort of like a large length scale, a length scale corresponding to the large eddies, where you have L is defined as k to the 3/2 over epsilon to the length scale characteristic in the large eddies. And we can define a Reynolds number REL, which is k to the half L divided by nu, or k squared divided by epsilon mu, using the definition of this part here. Okay, so you would have k squared over epsilon mu. Then you can define these microscales as follows. So lambda g over L, eta over L, and lambda g. So this now you have defined in terms of the Reynolds number. So at high Reynolds number, lambda g is intermediate in size between eta and L at very high Reynolds number. So it is not really at the small scales, but it is somewhere between eta and L. So clearly this has not been used a lot. And you will see that this can only be defined for isotropic turbulence, which is not practical anyway. So this is purely theoretical in that sense. And you can see that it does not have a clear physical interpretation. All we know is that it is between eta and L. But you can define what is called a Taylor scale Reynolds number by this one. R lambda is U prime lambda G over nu, which is traditionally used to characterize grid turbulence, because grid turbulence is used as an experimental data set in a lot of cases for correlating computations. So in that sense, it is used for a lot of different studies, mostly on a theoretical basis and not in a practical sense. So you cannot use it for jet flows or channel flows because it doesn't apply. The Taylor scale Reynolds number applies only to grid turbulence. So from the above equations, you can derive that R lambda in terms of REL. So in terms of a large scale Reynolds number, you have R lambda equals 20 over 3 REL, the whole thing raised to half. And you will realize that lambda G over U prime is square root of 15 tau eta, where tau eta happens to be the Kolmogorov type scale. And from all of this, there is also something called a velocity derivative skewness, which is defined as follows. So these are different applications of how when we started with the Kolmogorov hypothesis, we looked at the spectrum, but we started to look at some more applications where we could apply it to the Kolmogorov hypothesis. Meaning, we started with the autocorrelation function. Then we looked at, we actually started with the velocity derivative, the second order structure function, isn't it, of the velocity differences. Then we looked at the autocorrelation function. And now we have looked at a new concept like a Taylor microscale, which does not have a lot of practical utility, but it's still used in a lot of theoretical studies. And in fact, for grid turbulence experiments, which are primarily designed for validation of computations. So that ends this particular module, where we learned a lot of things about Kolmogorov's theory and its applicability to scales. So this is part of the module where we talk about the different scales. We'll now go to the next module in the next class, where we talk about part B of this, again covering more of scales and starting to look at Fourier transforms. Thank you.